How the success of the PIRE will be determined by Spencer Dansereau.
That's a lot of pressure.
No pressure.
No,
Yeah. So, yeah, I'm working in University of Colorado Boulder in the Aerospace Engineering Sciences Department under David Marshall, co-advised by Francisco Lopez Jimenez, who does ablation as well as high-strain composites for deployable structures on spacecraft. So I'm going to start off just by giving a little bit of discussion of some of the projects that we do in the aerospace department. Ellie used to work in our lab, so we heard from Ellie yesterday, looking at failure mechanisms in ceramic matrix composites. And this is a really important, knowing the fracture is incredibly important for both CMCs as well as ablative thermal protection systems, which is another facet that we do in the lab. We do everything from somewhat large scale, so tens of centimeters, down to looking at CT and SEM images, looking at microstructure and looking at fracture-driven microstructural failure. And so I just have a couple slides on some of the ablative work that we're doing, because it is pyrolysis driven. The energy dissipation methods in these heat shields, you can see on the left. This is a heat shield that is going to Venus. I mean, we're doing it on Venus. This one's to Titan, Dragonfly, and basically it's a phenolic resin impregnated carbon ablator, pica, and as that phenolic is exposed to very high temperature and very high heat flux, it undergoes pyrolysis, and that is the main energy dissipation method. And it's almost like this aerogel. And so we have this very, very porous matrix inside of a ceramic fiber preform that is pretty, I want to say, messy. It's the structure of it is considered random to date for modeling purposes. However, it's not fully random, and that leads to spallation, these sparks you can see coming off, but also large failure. And so one of the things we do in the lab is looking at these large chunks coming off and fracture and how that's driven from a microstructural standpoint. And not going to go into what we do on the image processing side, but basically we take these CT images similar to what Ali was talking about yesterday, where we construct these 3D renders using X-rays. So we shine light through the composite as it rotates around. And we take shadow images, and then those shadow images at different rotations can be reconstructed in 3 dimensions. We can then look at some of these layered structures that we see in these composites and do some analytical quantification as well as both qualitatively and quantitatively we can analyze these. But today, for the PIRE, we're going to be talking about a fabrication method that Rishi started along with Azarnush and Zoli. I guess it was 2015, 2016, at the University of Colorado with Professor Raj. And a few slides with some background of CMCs, then we'll get into this fabrication method, look at some PSEM photos. The CMCs, of course, are used in the aerospace and automotive sectors for high heat flux. Today, we're just going to be looking at silicon carbide microcomposites, because they have good oxidation resistance, as well as good mechanical properties at high temperature. And there are a couple different methods to produce a 6-6 composite. Chemical vapor deposition, you can do melt infiltration, which is what GE uses. However, melt infiltration is limiting at extremely high operating temperatures because you get free silicon in the matrix, which can break down the fibers as you undergo mechanical stresses. So that's not ideal for operating temperatures above the melting temperature of silicon, which is about 1400 degrees Celsius. And so PIP, or polymer infiltration pyrolysis, is the way to go, and we've heard several people talk about PIP before. Typically, you take a ceramic fiber preform, whether it's SiC or carbon fiber, others, and you infiltrate it with polymer for directly down to SiC, typically SMP10 is used, and you re-infiltrate this several times because you get shrinkage. And SMP10, as we know, as it shrinks, you get cracking. And this isn't great for matrix fabrication. Of course, this image is just a first infiltration cycle from some of the samples from Shakir, I believe it was. But this is just a good example of shrinkage of SMP10 if you just put it onto a microcomposite. Of course, you can re-infiltrate this. However, it takes time to actually have the matrix material undergo this process, as well as you can't control the porosity. And if you're trying to control the porosity, say for an active cooling application where you want to push cooling gases through, or you want to add different layers in with your composite, which we'll get to right at the end of some of the current endeavors we're doing. Say if you want to add hafnium or particles into the matrix, being able to control how you build up a matrix and without it cracking is potentially a useful thing to get after. And so just want to talk a little bit about when we do these thin layer deposition. So when I talk thin layer, we're doing layers that are thin enough that it's not cracking. And the cracking is really driven by a process very similar to you would think of in paint or mud. If you have a very thick like bottle of paint or bucket, as it dries out, as the water is evaporated, you get these stresses in plane that cause cracking. So the stresses in plane are beyond the fracture strain of fracture stress rather of the surface in plane, and so you get these fractures. And the same can be shown with just neat SMP10. So if you look at say this is basically just a vat of SMP10 in which a plate of fiber preform is lowered into it, and you can see that at very thick areas of SMP10, you see this large cracking, and as it gets smaller, that cracking gets smaller and smaller until you reach this critical thickness. Now, the critical thickness is pretty hard to define exactly between the green and ceramic phases, and we haven't dived too deeply into that. Mostly we've been taking from the critical thickness of the green SMP10 and doing about 1 to 5% of dilution, because we can get this thin layer by diluting the CMC, the pre-ceramic polymer, in a solvent. We use hexane or toluene, and this allows us to either dip or deposit the solution onto the sample, and we get a nice thin layer. And like I was mentioning earlier, this work was originally started manually in Dr. Raj's lab a number of years ago now, where they on carbon fibers use Sarset to deposit these thin layers onto the matrix material, the preform material. Again, they were doing it manually, so they are basically taking a syringe and then letting it dry, using a heat lamp for pyrolysis, cooling it, and then repeating the process. And so the first goal here was to automate that, but then there's a few shortcomings in using a furnace for this process, which basically, if you have a larger sample and you put the sample in a furnace that stays at 800 degrees Celsius because you want it to be quick, and the layer is so thin that the process is happens very quickly. I mean, about 30 seconds for the pyrolysis to happen. You basically sear the outside like you would like a tuna steak. So you have the center material doesn't undergo pyrolysis at the same rate. And so we moved to a different heating method, which is microwave heating. So the furnace process, basically, it's on a track, so the sample actually moves between the furnace and cooling chamber We have a 350 C cross-linking furnace as well, just to have it dry very quickly. And then some SEM images, which some of you may have seen some of these before, of some of the initial samples that we did with the furnace. And you can see we have some cracking as the material is wicked into the small radius of curvature areas between the fibers as the matrix begins to be built up. The contact angle is fairly low for these, for the solution beforehand, so it gets wicked into low radius of curvature areas, which can be beneficial for these cracks as well as voids that have kind of bottlenecked down and then open up again. It allows for the material to actually wicked in, so as the radius of curvature is fairly large at the bottleneck and then it opens up and you have a small radius of curvature, it actually the surface tension pulls in the polymer. And so you can actually build up those pores as it's being built up. So this can be advantageous even if you do have surface cracking, which we'll see in a little bit later, that you can actually get a fairly fully dense matrix. But again, this is just these small microcomposites. Basically take one toe of nickel type S, high nickel type S fibers, and then infiltrate them with this preform. But again, we have this searing problem. And so we moved to microwave heating. Microwave heating has been used on SMP10 before, as well as silicon carbide heating. You can even have microwave silicon carbide ovens that you can get on Amazon. Basically, it's silicon carbide powder on the inside. And the reason why silicon carbide is really good at heating is because it's a semiconductor. And so the skin depth, or rather the power distribution across the depth of silicon carbide is very large at 2.45 gigahertz, which is essentially the microwave frequency of a standard kitchen oven. What it does, the magnetron inside the like a kitchen microwave pulses at 120 hertz at a power frequency at 2.45 gigahertz. And so you get this power distribution. This is across a 5-centimeter slab, but the heat distribution is fairly good here. And this is again for a 70 watt per centimeter square centimeter incident radiation. And so it heats up rather quickly, and we don't even need to go up above 1,000 degrees C here. So we can heat it quite quickly. We've just been setting it to about a minute, and it's pretty good. This specific, they were looking at sintering, so it's also been used for heating silicon carbide for sintering applications. But this is just the slab here. And so we built a test setup and automation setup here, such that we can fabricate these samples under microwave in argon. So basically we have the same automated syringe that we had from the process in the furnaces, except the sample isn't moving this time. So we have a borosilicate tube and then another borosilicate tube that drops the polymer down, and then a cooling fan that blows cooling gas into cooling argon into where we're running our sample. And then one of the things that's really interesting phenomena, and I'm not an expert in the field of when we heat up, if you have anything that can arc, especially if you're using carbon fibers as your preform, it'll arc between some of the carbon fibers, and you can get this argon plasma. And as soon as it ignites, quote unquote, ignites, the whole borosilicate tube fills with argon plasma. And so there's some interesting physics that we haven't fully investigated as to how that might affect heat transfer into the sample. But that's why you see this, the whole borosilicate tube glowing in the picture on the right. And so we can produce samples again for this process. As we build up the matrix, we can get these fairly uniform layer depositions across the fibers. And this allows us to, again, control the porosity of the matrix. And it also allows us to look at the layer thickness. You can't really see super well the layers here a little bit. But this is on just a fracture surface, again at 5% SMP10 and then 1% SMP10. Again, these are high nickel type S fibers. So we're seeing 600 nanometers and then about 800 to 1 micron layer thickness. As far as, so this is increasing layer direction, increasing cycles. One of the things that's really interesting is that we haven't done a rigorous analysis on yet is why we see differences, or rather, can we predict what the layer thickness is going to be? Which is a very difficult question because we have the number of fibers that are touching each other is you can give a statistical distribution for, but anytime the fibers are touching each other, it creates an area of small radius of curvature. So you're wicking in more material into that surface, that fiber interaction surface. And so once the matrix is built up to the point that you have a fairly uniform distribution of radius of curvature, you can get a nice layer thickness distribution. But getting a really accurate amount of polymer that you're putting in and comparing that to what you would expect a layer thickness to be, we've had some difficulties with that to date. So at 50 cycles, we can fully infiltrate the sample. Can't see super well, but there are some cracks on the surface here. But when we look closely, we can again see some of the cracks on the surface. On the fractured surface, the material is pretty uniformly infiltrated. We do see, because this is not a woven sample, it's just a single fiber toe, again, uncoated, so no boron nitride coating on these. We can see large areas that were not filled in where it was not, the fiber packing density was quite low. But we can see some of the fibers here, like this is a good example of some of the fibers and then the wicking of the polymer as it's being infiltrated in between. And so one of the things that's pretty interesting about this process is this took less than 20 minutes to fabricate, from me putting the sample in to me taking it out and being able to analyze it, take it over to the SEM. So it's a very, very quick process, which has some promise in, especially if you do very low percentages, you can modulate your porosity, again, for cooling applications or filling it up entirely. So one of the things that we're interested in is how well the bond is between the fiber and the matrix. And so these are the unbonded fibers allow for looking at fracture between the fiber and the matrix here. So the next step really is we want to take some really good cross-sectional images with ion beam milling. Allows us to get this really nice smooth surface, as well as we've just started looking at adding hafnium as well as zirconium oxide particles into the matrix, and that can allow for not only materials reasons for oxidation resistance, the ultra high temperature ceramic oxidation resistance, but also it shows up very nicely under SEM, so you can get a really nice visualization of this layer distribution as you build up layers. These are both from CVI processes. And yeah, that's one of the project that we're working on right now, that carrying on some of the work that was done by Dr. Raj earlier.
Time for questions. I wonder how reproducible these parts are when you make it one by one.
I mean, first in terms of microstructure, that's probably the reason why you want to do markets. But second, also in terms of mechanical properties, we all know that ceramics fail according to weakest link theory or whatever.
Yep.
Can you comment on this? If you would test 10 pieces of which you made yourself, how big is the schedule in terms of mechanics?
Yeah, so I think one of the really important pieces is controlling impurities in the process. So when, for instance, when we were initially doing the furnace work, the sample stage was copper originally, just because it was easy to manipulate so that it was lined up right. But we ended up with little bits of copper into the layer because it's at the submicron level, which was a big problem. We'd see it under SEM. And so I would say controlling how making sure there aren't any impurities, but also we're just taking these single toes at the moment. And because it's not woven and they're not tight together, we're not holding them together, the distance between the fibers can be huge. So I would say right now, and like samples we're actually doing, there's probably a fairly large distribution because we're going to get these fairly large porosities from fibers that are not close together, simply because that's how we're fabricating it right now. But one of the next steps that we'd like to do is take small coupons. We have some three-dimensionally woven, some integrated textile ceramic type high nickel type S preforms that we'd like to infiltrate to get a little bit more uniformity. But it's a good question of how big is the mechanical property distribution? Can we accurately repeat a layer thickness, or is it really large differences between when the fibers touch each other? Does that really change mechanical properties? Can we get an accurate temperature each time? One of the things that we noticed earlier is because the microwaves can get up to very high temperatures, we actually would see some crystalline growth because the sample would get well above 2000 degrees C, which is way too hot. So that's why we back down on the microwave power. But yeah.
So this is on single tower.
Yeah.
So even with the single tower, you're seeing kind of porosity, basically from wicking.
Yeah,
right?
between the fibers, but
no.
Yeah.
Let's go back in that. But when you consider about the actual CNC fabrication in terms of either unidirectional mat or can buy dry fabric or woven fabric, how do you think that will translate these kinds of defects translate into those kind of woven fabric when you?
So I think a big piece of it is going to be choosing the right dilution percentage. So right now we're doing about a micron, but you can do it much thinner. You can do down to 500 nanometers or even less, 200 nanometers per cycle. And at that rate, you can potentially, especially with this low contact angle and wicking the polymer into these cavities we might see a better buildup of the cavities where the fibers aren't necessarily right next to each other. Say in a woven composite, when you have your waft and weave going next to each other, is going to be a distance between those two toes as it's being woven together. So it's a good question for when you're actually looking at doing a textile based ceramic preform of making sure that you get the right thickness, and also you can potentially change the polymer dilution percentage as it's being fabricated. We have the ability to do that in the lab, where basically we have a smart syringe that can pull from different sources, so you can have different solutions that you can program the system to pull from different solutions. So that's another dial we can turn to work on some of that. But it's a really good question for sure.
can also do it for multi-plies.
Yeah, as in like do different plies separately and then merge them together.
I
or-
don't know, that's what I'm asking.
Yeah,
Like, when you're trying to industrialize some classes.
Mhm.
One of the best thing is, what I see from your work is to interface to the PDC
right.
and when you can control the dilution of it, then you can have different coating interface coating that you,
Right,
because you're already crystallizing can go about 1000 degrees. That's what I'm saying.
right.
If that is the case, I think the best suit the best for interface coating and probably, still in the early stage, I can see that the aspect of knowledge.
Yeah, for sure, definitely.
Any other questions?